Hello, welcome to week 6, where we've started the class off with an introduction about basic hydrology, water law and such, moved through physical. Now we're into the chemical section of water quality before we move into biological. And so we're going to move through total dissolved solids as they go through the hydrologic cycle. We'll talk about major dissolved constituents and ion balance, total dissolved solids inverse relationship to discharge, quantifying TDS with specific conductance, and then revisiting different pathways to streams and the water quality implications. So if we look at this grainy crystalline substance here and think about it dissolving into water, if it is sodium chloride or table salt, then you've got your positive cation of sodium and your negative chloride anion, and it dissolves by dissociating, and then the negatively charged portion of the water molecule on the oxygen makes this hydration circle around it and dissolves it, and the opposite is true for the anion, where the positively charged portion of the water molecule, or the hydrogen end, make these circles around it. And so this is dissolution. We can easily think about that as a dissolved constituent. But what about sucrose, where it actually the molecule doesn't dissociate? It actually just comes into. But we know that sugar dissolves. So I think what's happening there is that you have small positively and negatively charged portions of the molecule, and the same thing happens where the water molecules orient around it to dissolve it or make it part of the solution. So as opposed to suspended solids or things that are just kind of floating around in there, dissolved means actually incorporated into the matrix. And the analytical definition for suspended solids was that it was retained on a 2-micron filter. And for analytical purposes, one definition that is commonly used is that dissolved is the portion of solids that passes through that filter. So you would actually then filter the sample, and then you'd have water and solutes in here, and you would dry that sample, and then the remaining solids in the bottom of that beaker are the dissolved solids. And 2 microns is pretty large, so there's actually going to be things in there that are not dissolved in that classic sense, but it's an analytical definition. It's pretty common for total dissolved solids to be casually referred to as salinity. And salinity is the concentration of dissociated ions in solution, but dissolved solids are mainly those inorganic ions. So this is not a completely misguided norm to do this, but it is important to remember that this analytical difference of total dissolved solids does not perfectly align with the salinity. There is going to be other stuff in there. So just a little bit about concentration notation. Thus far we've been talking only about mass concentration, or mass per volume, with units like milligrams per liter. In the case of our stream samples, where we've got really low concentrations, really dilute solutions, milligrams per liter is equivalent to parts per million. If you get up to sea level concentrations, where the solute starts to become important in the weight, then actually these two things are not equivalent anymore. But as far as we're concerned, milligrams per liter and parts per million are both equivalent. Once we get into molarity, we're talking about moles per volume, which is typically depicted with these square brackets. And this is the number of molecules of something per volume. And for stoichiometry and chemical reactions, molarity is definitely preferred over mass concentrations. And then normality is equivalence per liter. And so I'm going to walk through an example here. A silly example I like to use is that if we think about students in a classroom and we want to think about the concentration, we could weigh all of the students and think about what their total weight of students per volume of classroom was. If we want to start talking about the number of students, then that might be parallel to molarity. We count the total number of students, and that number over the volume of the classroom might be the molarity of students. Whereas normality might be if we were interested in the concentration of X chromosomes in the classroom. So at that point, we need to count the number of women and multiply the X chromosome by 2, and then count the number of men and multiply the X chromosome by 1. So men and women have different equivalents of X chromosomes, women having 2, men having 1. And so to count them up, we have to know whether we're talking about a man or a woman, and then how many equivalents of X chromosome they have. Kind of a silly example, but that's a distinction between these different types of concentration. So a quick overview of the range of values. Distilled water will have a total dissolved solids of close to 0, whereas seawater is about 35,000 milligrams per liter. World rivers average in at about 120. Estuaries are going to be mixing areas between these, so they'll be intermediate. The EPA has set a secondary drinking water standard of 500, at which point they say you could taste a little bit of salinity. I don't think you can really taste much salinity at that level. But the FDA has also set a threshold of 250 milligrams per liter for something to be able to legally be called mineral water. So just a couple of numbers there. We can't talk about water chemistry without looking at a couple of equilibrium reactions. So sodium chloride as a solid, depicted by the S here, is the example we've looked at. If you put that in water, then it becomes a sodium cation in aqueous form and a chloride anion in aqueous form. And we already talked about what that means as far as the atoms becoming dissolved in water. If we look at dissolving limestone, then we've got calcium carbonate solid in the limestone that combines with water as a liquid and carbon dioxide dissolved into the water, and that actually creates a carbonic acid which dissolves the calcium carbonate and produces aqueous calcium cations and one cation and 2 bicarbonate anions. So this is the process by which limestone is dissolved. You create karst topography and caves, things like that. Another formula here is for the dissociation of water. So a small portion of H2O molecules are constantly dissociated into the positively charged cation, or the hydronium ion, and the negatively charged hydroxide ions. And these two equations are just this two different ways to write the same thing. And so it's the balance between these that gives us the pH of the water. So the total number is always the same, but the balance between them is what gives us high concentrations of hydroxide give us low pHs or acidic conditions, and the opposite for the hydroniums give us high concentrations, give us basic conditions. So these are just a few examples. Obviously, we have myriad possibilities through the periodic table for ionic bonds dissociating into aqueous solutions. And to think about the implications for ions in natural waters, there's two things that have to be that have to occur before you're going to get a lot of something dissolved in water. And one is that it has to be abundant in the geosphere. So you've got to have a lot of it around to be able to be dissolved. And then two, you have to have it has to be highly stable as a dissolved aqueous species. And so these are the elements that, or the molecules that meet those criteria. So sodium, potassium, calcium, and magnesium are the cations. And then chloride, sulfate, bicarbonate, and carbonate are the anions that are the most common in surface water. So they're abundant on the surface, and they're also stable as dissolved species. There are a number of others, obviously. These are some of the more common others, but there are obviously a number of things that can be dissolved in aqueous solutions. And so if we start with rainwater, is rainwater completely pure? Well, it is at the point where it's evaporated, but as it moves into the atmosphere, there are aerosols and other constituents that can become dissolved in that rainwater. And so this is an example from the Boyd reading of rainwater chemistry in Northern Europe, and we can see that there's 10 milligrams per liter, not a negligible amount of total dissolved solids in that precipitation. And if we look here actually at the constituents, sodium and chloride are a big one. And there's a lot of sodium chloride in sea spray. And so if you think about waves hitting the rocks and blasting all of that water, salt water into the atmosphere, that's a good possibility for where some of that sodium chloride comes from. If we look at the rainwater chemistry from the central United States, we can see similarly high total dissolved solids, but nitrate is actually a big part of it. So we know that there are a lot of agricultural activities and in the central United States, and some of that nitrogen gets into the atmosphere and is precipitated back down as rain. The sodium chloride is smaller in the central U.S., a little bit farther from the coast, so that makes sense. If we look at large river water chemistry, we've got about 120 milligrams per liter, I mentioned before, is the world average. And they have combined here the bicarbonate and carbonate because these are actually part of the bicarbonate chemistry. And so depending on pH, you'll either have carbonic acid, bicarbonate, or carbonate as dominant in solution. So they've combined those, which are the dominant anion, and then we've got sulfate, chloride as the other anions, and then calcium, magnesium, sodium, and potassium as the cations. We also then have some silica oxides from dissolution of quartz and sand-type substrates. So this is all covered in the Boyd reading, but by looking at the big rivers, you basically are averaging the chemistry for the whole planet, because big rivers are basically averaging a bunch of small rivers. And so you get these relatively stable numbers down here. Whereas if we look at small watersheds, for example, the Mosier River in Nova Scotia, we have relatively low total dissolved solids. And if we look at this, it is a relatively hard, highly insoluble rock and relatively low total dissolved solids. Whereas if we look at the Withlacoochee River in Florida, we have higher total dissolved solids, higher than that world average in large rivers, and we can see that we're dominated, as the world's large rivers are, by bicarbonate, carbonate. And so Florida gets a lot of precipitation, so heavily weathered landscapes. And so a lot of the salts have been pushed through a landscape like that, but we still are getting these high concentrations largely attributed to calcium carbonate. It's a limestone geology, so this is dissolution of limestone that is contributing a lot of this total dissolved solids in that watershed. In contrast, if we look at the Pecos River in New Mexico, this is a very arid landscape, so it's not heavily weathered. The precipitation has not pushed a lot of the salts down through the system and into groundwater or out into the rivers. We've got small amounts of precipitation coming in, and there are a lot of salts that are still there to be moved out. And so we have a lot of sulfate here, and sodium, calcium, chloride, and so a very high salinity in that arid landscape. And so this represents the fact that in smaller watersheds we can see very highly variable total dissolved solids concentrations and makeups because of the different geologies, but then this all gets averaged into the large rivers. So what do you guys think lake chemistry looks like compared to these rivers? Well, for one example, Canyon Ferry, this is, I would say it depends on the type of the lake. So Canyon Ferry is actually, it's a reservoir on the Missouri, and so it's a long and narrow lake. It's relatively well mixed with comparison to, say, the Great Salt Lake. So the chemistry in Canyon Ferry is relatively similar to the inflow and outflow, whereas the Great Salt Lake is an internally drained basin. It's from what was classically Lake Bonneville, which drains, which is in the Great Basin, which drains a lot of Utah and Nevada. And there's no outlet to the Great Salt Lake. So we've got a number of rivers flowing in, but then the only way water gets out is by evaporation. And the concentration of salts in this lake are between 105 and 175 milligrams per liter, so 3 to 5 times saltier than the ocean. And so if we think about that, do you think that those high concentrations are simply the same as what comes in the rivers, just more concentrated? They're not, because we get such high concentrations here that actually things start to become past their solubility point, and you start to get salts precipitating out. So what we're left with are the salts that are most soluble, thinking about our criteria for what are dominant ions in water. The soluble ones the most soluble ones are sodium and chloride. So the lake is actually dominated by sodium chloride. Jumping down to the oceans, we see that phenomenon I just talked about represented in the oceans. So all the rivers flow into the oceans, but we don't see the same chemistry in the ocean that we see in the rivers because you've got precipitation occurring, and so it's this very soluble ions that dominate the chemistry. So sodium chloride, we still have a lot of these other constituents, but the 35,000 milligrams per liter concentration that we have in the ocean is dominantly sodium chloride. So as we think about the global water cycle, it is coupled intimately with biogeochemical cycles of other elements. So it's starting in rainwater, we have a little bit of constituents falling out that way, and then water travels through and across the landscape and results in these types of concentrations of elements in our world rivers, and then they carry those down to the oceans where we've got the vast majority of the water on Earth and a big reservoir of all of these constituents. So biogeochemistry is the science of coupling the fluxes and reservoirs of all of the Earth's constituents through biological, geological, and chemical pathways. And we are taking, in this class, a water-centric look at these biogeochemical cycles. Something that is really critical to point out is that water is a neutral substance. It has no net negative or positive charge, and so we can conduct something called an ion balance. And basically, to this point, we've been looking at the concentrations of solids in the world rivers in mass units of milligrams per liter, but we know that water is net neutral. And so sodium chloride dissolves in water to produce sodium and chloride, cation and anion, and those two charges balance one another. So if we look at this same data for the world rivers with different units of milliequivalents per liter, then the anions and the cations are split exactly down the middle. The cations perfectly balance out the anions. And so this relies on that equivalence, the units of equivalence I'd mentioned. For X chromosomes, we have to count up the total amount of negative charge and the number of molecules that are negatively charged, sum those up, and then balance them with the cations on this side. This can be a useful concept in a lot of contexts. One is to determine whether or not a lab report is accurate. And so for an example here, if you've got a lab report that says you've got 11 milligrams of magnesium, 50 of sodium, 78 of chloride, and 44 of sulfate, is it accurate? We can use our mass balance, our dimension analysis skills with mass balance to think about whether or not that's accurate. So we start out with our mass concentration given by the lab. We need to know the atomic mass of that atom or molecule, which is grams per mole. How many grams are in 1 mole of that substance? A mole is a number of molecules, Avogadro's number. And then what the molecular charge is on that molecule. And then we can walk through this, and so we start with the mass of magnesium per liter. We convert from milligrams to grams. We convert from grams to moles. Then we convert from moles to the number of molecules, just to be completely consistent here with the dimension analysis. Then we go from molecules to the charge on the molecule, and we can multiply that out, cancel the units, and we get charge per liter from the magnesium. And then we can do the same thing for sodium, the other cation here. We go from milligrams per liter to number of molecules, charge, and then we come up with the total charge in the water sample per liter from sodium. We can sum those charges from cations and get our total positive charge. And then we can do the same thing for our two anions, chloride and sulfate, sum those together, and then we can calculate a percent difference between those two numbers, and we get 1.1%, suggesting that that lab analysis is accurate. And if we look at this, actually, the charge between magnesium is very similar to that from sulfate, and that for sodium is very similar to that from chloride. And so we could assert from that that the salts that went into making this solution were sodium chloride and magnesium sulfate. I walked through the same process with the numbers provided by Boyd for the major constituents in world rivers. So I totaled up the positive charge from these four cations and the negative charge from the anions, conducted a percent difference, and it's negative 1.86. So 5% is a threshold that is often used for a percent difference that looks good, and so this means that this is believable inventory of the major ions in world rivers, because the ion balance, the charge balance, pans out. So if you get a lab result or a chemistry for a water and the charge balance does not equal out and the percent difference is greater than 5, either negative or positive 5, then that means one of two things. Either you have a large constituent, an important ion that is not accounted for, or the lab results are wrong. There's exactly two possibilities, because water is always neutral, so either you haven't accounted for something or one of the numbers is incorrect. I'm going to jump to another equally important but very different characteristic of water, that is electrical conductivity. The silly example I like to use for electrical conductivity is that if you're taking a bath with a radio perched precariously above you on a shelf, would you want to be taking a bath in distilled water or seawater? And the answer is distilled water, because it's the ions dissolved in solution that conduct electricity. Pure H2O will not conduct electricity with a meter like this, perhaps. And so this meter, what it's doing is passing electricity between these two electrodes and seeing how much resistance there is, or how much electricity makes it through the solution to the other electrode. And that's a function of two things. It's a function of the total ions in the water, and it's a function of temperature. And if we're trying to use electrical conductivity as a surrogate for the total amount of salt in the water, then we don't want interference from the temperature. And so we have to measure both temperature and electrical conductivity and correct the EC for the known effects of temperature. And this is pretty easy to do because we know the relationship between temperature and increasing electrical conductivity. But so if we want to use it to estimate the amount of ions, then we need to go from electrical conductivity to specific conductance. And specific conductance is the electrical conductivity corrected to 25 degrees C. Okay? And so an example of what that looks like is if we measured both electrical conductivity and specific conductance over these months through the year. In this case, conductivity, the raw conductivity, is always lower than specific conductance. And but some of these numbers are much closer together than others. And so if we put temperature on here as an explanatory variable, then we can see that these green bars are the temperature over here in degrees C, and as the temperature approaches 25, the electrical conductivity and the specific conductance are pretty close together. When the temperatures are low, the numbers are more different. And again, in all cases here, the electrical conductivity is less than the specific conductance, because we're always below 25 degrees C. Hypothetically, if we went out and collected electrical conductivity and specific conductance, and the electrical conductivity was larger, then we would be able to know that the temperature must be greater than 25 degrees C. So this is just to underline how that relationship pans out between electrical conductivity and specific conductance. So a meter like this is going to tell you that they're giving you specific conductance. These are some of the units: decisiemens per meter, millisiemens per centimeter, microsiemens per centimeter. Those are all conductivities. This is a resistance, actually, 1,000 microohms per centimeter. The most common units I see are decisiemens per meter and microsiemens per centimeter. They are off by 3 orders of magnitude, so you do need to pay attention to the units you're looking at. This meter will also tell you that it's giving you total dissolved solids. Is it giving you total dissolved solids? No, absolutely not. We saw before that total dissolved solids is analyzed by filtering, drying, and weighing the remaining solids. This meter is not doing that. It's passing electricity between those two electrodes, and then it's estimating the total dissolved solids from a relationship. And it does that based on the fact that there are pretty good, well-established relationships between the total amount of dissolved solids and the conductivity. They are slightly different for different ions, but on the whole, this is the data plotted for a lot of the data for our well test program conducted across Montana, and we can see that in this case, our relationship has a slope of 0.70, which means that our conversion would be 704, where the one on the previous page was 640. So people will typically use I've seen people use anything from 0.5 up to 0.8 for a conversion factor, and they can be different in different places. If you want to take a conductivity number and quickly get to a total dissolved solids number, you can just half that number. It's the simplest math. So 3,000 microohms or microsiemens per centimeter is going to give you 1,500. Is just a quick way to do the math. And this is an extremely reliable method for estimating total dissolved solids. So the actual coefficient for the conversion can vary a little bit, but it's an extremely reliable and useful method. So I want to come back to this concept that we had in the hydrology lecture of overland flow versus subsurface flow, just breaking it into two really simple possibilities, and that particulate moves over the surface. Dissolved can also move over the surface, but it is only dissolved that moves through the subsurface. So thinking about looking at this data for the Yellowstone that you had in week 5, this is presenting it in a slightly different way, both as time series. So you've got your sediment here in brown that's on this axis, and your hydrograph in blue, which is on this axis, and you can see that the highest sediment is corresponding to the highest discharges. And we saw that represented in the rating curve for sediment that you use for your homework, that showed that the highest discharges have the highest sediment concentrations. And this is a result of, at those highest flows, you've got more overland flow, more water moving over the surface, and more power in the stream, and so you've got higher concentrations of sediment at the higher parts of the hydrograph. This is in contrast to things that move through the subsurface. So if we're talking about dissolved solutes that have moved through the subsurface, they are going to be the lowest at those high flows. At high flow, you have a lot of water moving quickly over the surface, and snow is melting. It doesn't have a lot of time to interact with the substrate to dissolve things. It has time to pick up particulates and move it off, but it doesn't have time to dissolve minerals. Whereas the water that moves down through and travels through these subsurface pathways could take days to centuries to get to the stream and has plenty of time to dissolve limestone and other minerals. And so at base flow, during the low time of year, you're getting flow from groundwater, from subsurface flow, and so low flow but high concentrations of solutes. Again, in contrast to when the flow comes up and you're getting more overland flow. The result is this inverse relationship between discharge and total dissolved solids. At the highest discharges, lowest dissolved solids. You're going to look at an example of this for the Powder River Basin in eastern Montana, which is an arid landscape. There's a lot of coal bed methane development there, and this USGS publication that's in supplemental reading talks about that and has data like this in it where it shows the hydrograph and that you've got the highest specific conductances in black here at the lowest flows. And so again, that inverse relationship. Another example that I just want to bring up, there's a couple of additional supplemental USGS readings that illustrate these points. That here we've got in Kansas, the hydrograph, when it peaks, turbidity also peaks, and the specific conductance dives as the flow goes up. And so we know that specific conductance is a good surrogate for the total dissolved solids, and is dominated when low flows dominate through the subsurface. We get those higher specific conductances, and alternatively, when flows are coming over the surface, we have less specific conductance but more turbidity, because the turbidity has picked up as the flow increases. A third USGS circular that's up in supplemental readings is for Maryland, and shows the hydrograph here increasing, turbidity at both of these sites increasing as the hydrograph increases, as we expect. But then we see something that is a little different up here. While this first site shows the behavior that we expect, the second site shows more complex behavior where the specific conductance dives, but that it increases, illustrating that there was a different flow path for this water that came through someplace where there was a lot of ions or salts to be dissolved and transported by it. So either that came across the surface and there were a lot of solutes on the surface, or through some kind of a shallow groundwater system or stormwater runoff system where there were solutes to be carried. And so this is indicative of these two different waters taking different pathways and picking up different solutes and different particulates as they move into this stream. And so these surface versus subsurface pathways are a critical conceptual framework for understanding the chemistry that you see in the streams, and then putting that all in the big picture of how all water and solutes and solids move around the planet is all trying to pull together this conceptual framework so that you can understand these things in any system you're interested in.